So today I'm going to talk about functional data structures in a language called Julia. And I'm using Julia for code samples, and that's where I actually did the work. But I hope that these ideas are more general than Julia, and that if you wanted to, you could take them and implement something like this in another language. So it's worth talking first about Julia, the language, before we actually get started with the data structures themselves. So Julia has MATLAB-like syntax, and it's poised as a language for technical computing, but I think it's a lot more general than that. Julia is a dynamic language, but it's also fast and has a nice JIT compiler. And Julia also has types. Now, the type theory pedants among us would want me to point out that what Julia has are runtime type tags, not compile time types, and that Julia types are used for performance and expressiveness as opposed to safety or correctness, as you'd see in a language like Haskell. The primary unit of abstraction in Julia is called the generic function. A generic function is a first-class function that dispatches to a particular implementation based on the types of all of its arguments. And you use these pervasively throughout Julia for extending your own data types to built-in functionality in the language. So let's talk about generic functions really quick and what you can do. First, we're going to define a data type. This is an abstract binary tree. Has a concrete type, which is a node. That it's immutable means that once I create these fields, they cannot change. I couldn't say my new node.data equals something else. Once I have it, it's this immutable value. So node is a binary tree. It has some data associated with it. It also has a left and a right tree. That has to be a binary tree. So we have two concrete types of binary tree, which means that the left and right field of node are either going to be another node or a leaf. We're at the bottom of the tree. So a leaf just has some data associated with it. We can create a new one of these binary trees like this. Something that might be useful is asking, is the number 3 in my binary tree? So in Julia, this syntax, 3 in some binary tree, parses to something like this. So I have base.in. Base.in is a generic function in Julia's core library. And it's going to pass in the item that we're looking for as the first argument, and then the tree that we're searching in as the second argument. So if we want to implement in for our binary tree, we can do it like this. Here we're saying that if the first argument is some data and the second argument is one of our leaves, then we see if that data is contained in the leaf by asking if that data is equal to that leaf's data. Our recursive case is the case of a node. So we first say, is this data that node's data? If it isn't, then is it in the left side of the tree or is it in the right side of the tree? And once we have this, we can kind of partake in this built-in syntax in Julia. So this is kind of how we use generic functions to extend our own data types to the syntax of the language, and we have this kind of nice extension. Now let's talk a little bit about functional programming and functional data structures. I think a precise definition of functional programming is a little bit elusive, and people like to debate it, so I'm going to totally punt on it. Instead just say that functional programming encourages programming with immutable values, not mutable objects. The data structures of a functional language should support this. When you change one of them, it shouldn't actually mutate it. It should instead return a new value and leave the old one unmodified. This means that they're persistent. Old versions stay around. The data structures should support multiple versions of the same fundamental thing. They should also be fast, and they should guarantee the same or roughly the same computational complexity characteristics of their mutable counterparts. Julia has some not functional data structures already built in. We're just going to move through a few of them really quickly. So I can create a new vector like this, and I can index into it. Something interesting here is that notice that a of 1 returns 1. It doesn't return 2. That's because Julia is indexed from 1. This isn't much of a big deal, but it will impact some of the code that we write a little bit later. I can push a new element into our vector, and then notice when I query the length, it's actually increased, it's mutated. So these are just arrays or lists like you'd see in any regular kind of imperative language. Julia also supports maps, which it calls dicts. And you can create them as you might expect. You can add new elements to it as you might expect. So this is pretty standard. Julia also has sets. I can create a set of the characters A, B, and C. This ellipsis is the splat operator, and it is going to treat the string as a sequence of 3 characters and kind of expand it out into the arguments to the set constructor. I can push another character into it, and I can ask if D is an alpha, and of course it is. Now notice that here I use push bang. This is the Julia idiom for some kind of collection mutating operation. Now what I want is something that's persistent. So what we're going to get pretty close to by the end of this talk is the ability to create like a persistent vector. I should be able to query it the same way, but when I push something into it, instead of mutating the original one, I should simply get back a new one. And if I ask the length of the original A, notice that it's still 5. I should also be able to do the same with maps. I should be able to associate a new key value pair onto an existing hash map, and I should get back a new one. But if I look in the previous hash map for the key Sir Robin, I don't get to know that he's not quite as brave as Sir Lancelot. And the same thing with sets. So this is all pretty standard. This is what you might expect if you were doing functional programming. But in case you haven't done a lot of it, this is what we expect these operations to do kind of once we're through with this. So let's do a quick, simple example of an easily kind of persistent data structure. People talk about a certain class of problems as being embarrassingly parallel. I think that the linked list is embarrassingly persistent. So here we have a linked list X that points to some tail. We don't care what the tail is. But we might want a new linked list Y, which is the result of consing some element onto X. And then we might say, well, I actually want a list Z, and Z is the result of consing some element onto the rest of X. Here we can see that all 3 of these lists are sharing structure. And this is really useful. We actually kind of want this property in our persistent and functional data structures. One, for space efficiency, because that means that when I create a new version, I don't have to hold in memory 2 copies of the same thing. But also for computational efficiency. I don't want to have to copy every single element over to my new structure just because it's immutable. That would be pretty awful. So Phil Bagwell, in I think 2000, talked about 2 different data structures, the array map trie and the hash array map trie. Rich Hickey, when creating Clojure, adapted these data structures and created something called a bitmapped vector trie, which is what supports Clojure's kind of persistent collections. I think it's also been used in Scala for Scala's, I think, collections.immutable namespace. Now, the bitmapped vector trie is a trie. A trie means that it's a tree where the data is in the leaves. And the nodes going down to the leaves represent a path to a certain piece of data. A kind of common example of this is a prefix tree used for string lookup. So at the top, you might have single characters, and as you get further down, you might have string prefixes, and this could be used for something like autocomplete. We're going to be looking at tries that work on the bitwise level, though, because what we want is a trie that represents some kind of random access array-like structure. So the nodes are going to take a peek at certain bits of the index, and it's going to lead us down to the actual element. So let's talk about a persistent vector. And this is where we're really going to get into the data structures. And the goal here is to focus more on the data structures at a high level. And while I will show some code, what I really want is for people to understand how these data structures might actually be implemented, so that it could be implemented in other languages as well. So a persistent vector is an array. And it's an array of a certain fixed number of elements. And this is just a mutable array like you'd expect in some kind of imperative language. Each one of the elements of this array are a bunch more arrays that are also of the same size. And they also contain the same types of arrays that are of the same size. And at the very bottom, we actually get real data. So here, 4 levels deep, we actually have the actual indices. In this case, this might be the data, but it happens to be the indices if we were indexing into this vector. But this is the high-level representation. Notice also that this thing is actually dense, so everything on the left-hand side would be filled in. And we can just pretend that everything is filled in, but obviously that would be too many arrows. A useful, or first we can talk about, I guess, the actual data representation. So we can look at some more Julia code. So we're going to have an abstract bitmap trie, and then we're going to have an array node. And an array node has an array, an internal array, which is a vector of bitmap tries. And it also has the shift value, which we'll talk about later. And then it has a length and a max length. The length isn't just its length, because all of them are going to be eventually length 4 in the case of this example. It's actually going to be the length that represents the number of elements that are in its leaves all the way down. And the max length is the total size that it can grow to before it needs to do something, and we'll look at what that thing is. Then we have an array leaf, which just has this internal vector. So let's talk about how we actually access something. So let's pretend that we already have this pre-built thing, and we want to access index 106. So the key insight here is that we can look at 106 as a binary representation, and let's pretend that we're in some world with 8-bit integers. So each level of the trie is going to take a peek at a certain sequence or a certain view of this index. At the very top, we're going to look at the top 2 bits. Then we're going to look at the middle left bits, the middle right bits, and the bottom bits. So this is really interesting. Notice that this series of bits corresponds to basically how to index down into the trie. So at the very top, we need to look at index 1, then index 2, index 2, index 2. And that corresponds with the actual binary. The math of this isn't particularly difficult either. At the top, we do a shift right of 6, and then we mask with, or we do a bitwise AND with 3, and that's to kind of mask off the top bits. So all we have to do is just change the number of bits that we shift to the right. And we get down to our answer 106. So let's define these bitwise operations. We'll have a couple helper functions, shift value. So the shift value for an array node is that shift field. So the actual nodes themselves are going to keep track of how far an index has to shift for them to look at the correct bits. An array leaf always looks at the bottom bit, so it shifts by 0. Then we can write our mask function. So remember that Julia is indexed from 1, and this bit math only works out if we are considering indices from 0. So the kind of easy solution to this is just to quickly decrement I before we do the math. So this is the same math that we saw before, where we have some index. We're going to shift it to the right by the shift value of that particular tree that we're looking at, and then we're going to do a bitwise AND with 3 to mask off the top bits. The reason also that we're looking at 2 bits and we're doing AND with 3 is because it takes 2 bits to represent 4 pieces of information, and our tries are all, each node has an array of length 4. And then we increment the view back up so that we're back kind of into Julia index from 1 land. So now we can implement getIndex, and what this will allow us to do is actually use the bracket syntax for indexing into something. And now this is quite simple once we have this mask function. If we're in a leaf, the way that we get the index is just by indexing into the internal array the result of masking the correct view. So this is really simple. There's a recursive case if we're in a node, where we have to mask the node index correctly, but then we also make a recursive call. Notice that there's this extra bracket of I, and that's because when we access an element from the array node's internal array, we're going to get back another bitmap try, and we want to continue down until we get to the very bottom and actually access an element. Now let's think about associating a new element with an index that already exists in one of these bitmap vectors. So the idea here, remember, is that now we're updating something that already exists, but we can't change it because we don't want to mutate anything. We need this previous version to be available. So what we're going to do is as we navigate down to the element, we're going to copy just the path that it takes to get down to it. So here, I can copy that top node, but notice that it's sharing the structure on the left, right, and middle right side of this new node. So we only need to copy the elements on the path. And we continue this process down until we get to the very bottom, where here I've replaced 106 with foo. Now this is really interesting. This is a structure that can contain 256 elements, and in order to update one and keep it immutable, we've only had to copy 16 things. That's pretty fast. Also, a quick thing, functional data structures are made with lots of arrows. So this is a pretty simple thing to actually code. If we're going to write our associate function for a leaf, all we do is we copy the internal array. So this bracket colon operation is like Python slice operations, just a way of copying an array and getting a new one back. Then in this new array that no one else has access to, we can actually do the mutating thing. So we just set the element in the proper thing, in the proper slot, and then we create a new array leaf with that new array and we return it. We have a slightly more complicated recursive case where we have an array node. So now what we need to do, we do the same copying, but notice that we have a recursive call on the third line of the function, where instead of just immediately adding the element, we have to associate the element with the child and then add that child into our new internal array. And then we create a new similar array node. We don't have to update anything, so we use the previous node's attributes to do that. So now the thing that we want to do is now, assuming that something is already constructed, we can get an index from it and we can update an index, but we have no way of growing this thing. So we need push. We need a way of actually increasing the size of our persistent vector. But push is a little bit more complicated. There are a few different cases that we have to consider when we're actually growing the thing. So if we're trying to push into an array leaf, we have to consider whether or not it's full or not. If we're trying to push into an array node, we have to consider whether its last child has room so that we could append to the last child, whether the last child is full, in which case we need to create a new last child, or whether the array node itself is full, in which case we have to create a new containing array node. So we'll go through each of those cases here. So here, we're going to push 2 onto a vector that is not full. This is really easy. We just do a copy, and we add 2 in. And so this was a pretty simple case. But what if we have a full array leaf, and we want to add 4 into it? In this case, we construct a new array node, the first element of which points to that previous leaf, and the second element of which points to a new child that contains 4. So whereas in this previous example, we did have to do some copying, here copying is actually, there's no copying really that's happening. And we're just constructing new things that can share the structure of that previous thing. And these are just one of the benefits that you get where everything is immutable. Now, if we want to push 5 onto this new array node that we've constructed, well, in this case, our rightmost child still has room, so we can just add it into that rightmost child. And the way we do that is by, again, creating a new top level and copying the path down and adding 5 in. Now, assuming we have 8, again, we just do kind of the same thing, where now our rightmost child was full, so we need to construct a new child and add it in there. And this is similar to the case where our leaf was full. If our node is full, then we just construct a new parent that points down to a final child. So this is kind of important. We won't go into the actual code of this because there's quite a lot. There's a lot of cases to handle. But it's pretty simple, really. What you need to do is nodes need to know how to construct children, and they need to know how to construct parents. And then they just look at themselves and their children to determine whether or not an element being associated in can just go directly in, or whether they need to do some kind of promotion or demotion. So the astute among you might notice that I never actually defined a persistent vector type. I held off on this and just defined a bitmap trie, because the persistent vector is going to implement an optimization. So the persistent vector has 3 attributes. It has an internal trie, which is a bitmap trie, and then it has a tail, which is a vector, and then it also stores its length, so we have constant access to that. So the question, though, is what is this tail? So in our examples, we appended our actual data directly to the trie. But what if instead we appended full vectors? So instead of appending data, we appended length 4 vectors. So all of the leaves contained length 4 vectors. This would be really interesting. Then what we would have is we would have fast access to the tail up at the top with our persistent vector. And one of the most common things you do when you're constructing large arrays is appending to the back, which also means that and basically what that means is that if our vectors are length 4, then we only have to touch the trie one out of 4 appends. Otherwise, we can just add to this tail. We do this copying that's very fast and very easy for us to access. So this is really nice. We only update the trie when the tail is full. Now, this would actually require some other changes to the code, because when you got the index, or when you asked the trie for the element at index 106, what you would get back is actually another vector. And so you would need to make sure that your trie leaves you some bits such that you can look in that final vector and get the element that you're looking for. But this is an optimization that has a pretty significant impact on your ability to add elements to the back of a persistent vector, to the point where it's something on the order of only 5 times slower than doing like push bang onto a regular array. It's quite fast. Now, we also don't really use length 4 internal vectors in an actual implementation of this. Phil Bagwell has this graph in one of his papers. Basically, when you're increasing the size of the nodes or of these internal arrays, there's a trade-off between indexing speed and update speed. So when the arrays are small, update is slightly faster because you don't have to copy as many elements when you're copying down the path. But indexing is slower because you have more steps that you have to go down when you're trying to get an element. And it just turns out that 32 tends to be a pretty good balance. In this graph, it looks like 16 might actually be a bit better, but I didn't do any testing. I just used 32. There's some further reading if you're interested in persistent vectors. So in 2011, there was another paper that came out, RRB trees, efficient immutable vectors. Bagwell saw some of the work that was done that adapted some of his older data structures to newer functional languages and thought, well, we could do even a little bit better than this. One thing that's a bit of a bummer with this adaptation is that concatenation is still order n. So you have these two trees and you want to concatenate them together. The way that you do it is you just pull all of the elements from one tree into the other one. So we created this structure, RRB trees, which stands for Relaxed Radix Balanced Trees. And these relax the length of the vectors and have a balancing operation that allows you to get log n, order log n, concatenation time. This is something that I haven't looked into enough yet to be able to describe in any more detail than I just did. But it's definitely a further place to go that could give you even better characteristics. There's a small trade-off with indexing and update speed. But I also think that there's a way, there's an implementation in Clojure that I think avoids this trade-off until you've actually done the concatenation. So it delays kind of promotion to this relaxed radix balanced version until you've actually done the concatenation. So in practice, it's not much of an issue. So now let's talk about hash maps. So we kind of have our first data structure out of the way, and we've seen how we can use a bitmap vector trie to construct something that is immutable and also is array-like. So how do you normally construct a hash table? Well, hash tables are built on array-like things. That gives us some indication that we might be able to use this same fundamental data structure to create our hash map. Mutable hash maps usually, common implementations, start at a fixed size, say 8. You insert elements based on some hash, and you look at maybe the bottom bits. So if we have a size 8, we'd look at the bottom 3 bits, and when we hash values, and we'd insert them in there. But you have to deal with collisions, because eventually, if you have 8 elements, it's likely that you've run into some collisions at that point. So what you commonly do is you resize the table when you're roughly 2/3 full to avoid lots of these collisions. And this resize operation has some cost, but it's amortized over the kind of lifespan of the data structure. And the resize might be like 4 times when you're kind of at small sizes. It might start doubling once you get a little bit larger. Our persistent hash map is going to also have to handle collisions, but we're going to do it in a way that avoids resizing altogether. And we're just going to kind of get immediately started with this data structure, just looking at how we add new elements to it. So let's pretend that we're on a leaf. With our persistent hash map, this is again going to be another trie, except that we're not really going to have a concept of nodes and leaves. Every single node has the ability to contain actual data or to contain pointers to further tries. And so here we have the very top, so it's going to grow in a different way from the persistent vector. Here we're at the very top, and we've inserted 2 keys. I'm just kind of ignoring the values at this point. But again, because we're length 4, we're only looking at the bottom 2 bits. So we have Sir Robin inserted into index 1, because those are his bottom 2 bits, and Sir Bedivere is inserted into index 2. Now let's say that Sir Lancelot comes along and he wants to partake in this hashing experience. So we're going to insert Sir Lancelot, but we have a collision. So what we're going to do is we're simply going to copy this kind of root, and then we're going to construct a subtrie. And so whereas index 2 previously pointed to Sir Bedivere, now it's going to point to another trie, and we're going to use the next set of bits to index Sir Lancelot and Sir Bedivere into this previous trie. So now we've avoided the collision. And if we want to, say, update Sir Robin's value, we can do that just as well. All we have to do is we copy that top-level structure. We can share that trie that we've already created that contains Sir Lancelot and Sir Bedivere. But now we have this updated version. And in all of these slides where we have some element in the background, all of those pointers are still intact. Nothing has actually been changed. So we do still have an immutable structure. The question that we want to ask, though, are what about these? So normally in a mutable hash table, you have these extra slots. They're basically just empty slots, but they're taking up memory, and they're there because you're going to resize much larger than the data you actually have, such that you can avoid lots of collisions. We actually have a kind of a nice thing that we can do with a persistent hash map where we can avoid this altogether. So what we're going to do is we're going to add a number to each one of these nodes. And this number is going to be the number of bits that is its size, basically. So because this particular node on the left has 4 slots, we need 4 bits. We're going to turn on the bits that correspond to entries that have been inserted into the hash map. So the bit on the far right is going to be index 0 and then 1, 2, 3. So in this case, 1 and 2 are on, so the binary is 0, 1, 1, 0. And we're going to do the same thing for this one over here. So now we have this bitmap that corresponds to entries that have been inserted into our hash table. Now, this might not be obvious, but what this allows us to do is totally collapse our structure and eliminate empty spaces altogether. So let's see how that actually works. Let's say that I want to access Serbedivir. So I hash that key, and I get this binary number on the right-hand side. Now, I want to be able to use the same kind of search strategy that we used with the persistent vector to kind of navigate down the trie and ultimately get to that key value pair. But unfortunately, notice on the right-hand side, I've highlighted 1, 0, which is 2, but I actually need to be indexing into 1 because we've collapsed, we've lost some indices. So let's look. So now what I've done is I've copied over the bitmap from the left-hand side, and we can first ask, does this trie have the index that we're looking for? And we do that because each one of the on bits corresponds to some index that has something inserted into it. So it turns out that if we look at the 0, 1, 2 bit, it's on, which means that we do actually have that index. What we can then do is mask off all of the bits at that index and above, and then do a bit count. So bit count is an operation that exists on most modern architectures, which is a very fast counting of the bits that are on in some sort of integer. So here, we get the true index. It just turns out that this trick always works when you have everything set up this way. We mask off the top bits, and then we do a bit count to figure out the actual offset and the true index. So now we can index and move on to the next thing. And just to show that it works, here we have the same kind of situation where we're looking at 2, it happens to be on, we mask off the top bits, we do a bit count, and we can access Serbedivir. So there's a couple different types that we need to create for this particular implementation. We're going to have a mutable hash map entry. And then we're going to hold on to the hash so that we don't have to recompute it later. We'll just store it. And then it has some key and some value. Then we're going to have a sparse bitmap tree. And even though it is actually compact, sparse is to indicate that we have some bitmap and that in reality only some of the indices in the internal array are on. So we can create a sparse array node. This vector contains possibly 2 types. It contains either more sparse bitmap tries, which in this case just happens to be more sparse array nodes, or it contains hash map entries. Then we have the same attributes that we saw on the regular array node for the persistent vector, except we have an addition of a bitmap, which is an integer, that we're going to use to basically keep track of what entries have been inserted. And then we define shift val. Because we've kind of have this contract that all bitmap tries should have some shift value, so that we can use the same mask function to figure out what kind of section of bits we should be looking at each point. Now we can do all of the bit math that we basically wanted to do before. So if we find, the way that we can find the bit position is by finding the 2 bits that we're looking for, or in this case it happens to be 2 bits, but finding the bits that we're actually interested in, subtracting 1. So if we were interested, if we happen to find bits that represented like 3, for instance, we want to subtract. Wow, there's complicated stuff. Anyways, so we get this mask, we subtract 1, and we shift a 1 up. And the goal here is basically we want a number which is something that is a multiple of 2, basically. And it's going to represent the single bit, which is the position in the bitmap. We can then ask if this index is on by doing an AND with that bit position. So we have this bitmap. If we do an AND with that bit position, it's only going to be something non-zero in the case that that bit was also on in the bitmap. Then we can determine the slot by basically doing the same thing, where in this case we're doing the bit position -1. So if our bit position happened to be 32, what we would get is 31, which would mask off the bottom right bits. And then we can count all of those 1s and then increment again because we're in Julia index from 1 land. So this is the kind of bit math that we need to do in order to use this kind of modified version of the vector trie. So there's some things that we haven't shown here. One is deletions. Deletions are actually pretty simple with a persistent hash map. Deletions are more complicated in a mutable version because usually you have to somehow indicate the way that mutable versions usually handle collisions are that if you go to a slot and it's full, you just look at a next series of bits and then jump to another slot. But when you do a kind of a get index, you first go to that slot and say, hey, this isn't what I'm looking for. I need to go to the next slot that it would be at. Which means that if you delete something, you can't just remove it entirely, because then when you go back and there's nothing there, you say, oh, this key isn't there, so I'm just going to give up. With the persistent variant, we never actually do this jumping around, so you can just delete things, and it's pretty trivial. You also do need to handle true hash collisions, so this is the case where two different values actually do hash to the exact same thing. This is pretty unlikely. I mean, in Julia, if you have a good hash function and you're getting back some kind of 64-bit integer, it's pretty unlikely that you're going to get true hash collisions. But a simple way of handling this would be to have another node type that exists in your hash map. It might be a collision node, and if you ever get down to a collision node, you have to do the kind of slower key comparison. You can't just do a really fast hash comparison. So now let's talk about persistent set. This was a bit of a lie. I said I was going to talk about 3 data structures today, but you just kind of wrap the map, right? A persistent set is really just a hash map where the values are nil. So this is really useful. And then you just kind of implement all of the regular set operations. But in this case, you basically get this third data structure for free just by creating this efficient variant of the hash map that happens to be persistent. Let's talk a little bit about performance. Lookups are very fast. Lookups are log 32 of n. When n is like 4 billion, that happens to be 6. So we're just going to say that it's basically constant time. This happens to do with the very large branching factor of the trie. If you think about what you're actually doing to access an index, let's say you have you have 7 layers of depth. You're doing like 14-bit operations and 7 pointer dereferences. So these are really fast things. Updates are a little bit slower because you actually have to do some copying. But if you do have, say, a full persistent vector that has billions of elements in it, you're still at max only copying like a couple hundred elements. And that's a pretty small price to pay to have immutability in such a large structure. There are some interesting, I think, conclusions that we can draw from this. Julia happens to be a really good language for creating these kinds of structures. Even though it doesn't have a static type system, its type system is pretty expressive, and generic functions make it very easy to extend new data types to the existing language. You also get a huge amount from this one fundamental data structure. All we really had to do was kind of understand this bitmap vector trie, and then with a pretty small modification, we were able to extend it to a hash map, and we get just kind of a lot just for understanding this one thing. It's also, I think, worthwhile thinking about creating functional abstractions in a mutable world. Julia isn't a language that comes with these things by default, but it's a language for which they're pretty easily provided. And I think it's worth exploring different ways to look at existing languages and find ways of extending them, maybe in ways that they weren't intended. So this is kind of an interesting example of this, where lots of our implementation had to do with mutation. We were using these underlying mutable things to create a nice functional abstraction. Now, I have a more complete implementation of these at Allaun/functionalcollections.jl. It's still a bit of a work in progress, but it has quite a bit more. If you're interested in more code, you can see it there. And that's it. I'm Allaun. I work at Hacker School in New York, and I appreciate you taking the time to listen to me.